All right, so this module is going to be about attacking the foundation. What they're going to be worried or looking at here, not worried, but what they're going to be attacking is looking at TCP IP vulnerabilities, the fundamentals of those, what different network attacks that are available, as well as those vulnerabilities for the TCP and UDP directly writing on IPv4. So for IPv4 and IPv6, as we've talked about with IP was designed as a layer 3 connectionless protocol. All it does is provide necessary functions to deliver a packet from a source host to a destination host over an interconnected system of networks. So IP makes no valid effort to determine whether the source address contained in the packet actually came from that source, and therefore threat actors can send packets using a spoofed source IP address. Those same ones can tamper with other fields in the IP header to carry out attacks, so it's important for security analysts to understand the difference between them in IPv4 and IPv6. So in IPv4, as we kind of refresh here, the first byte is going to have your version and internet header length, then byte 2, 3, 4, as you see on here, and then the 20 bytes down that goes inside of there. There's 10 main fields within an IPv4 packet, in this case a header. So as we mentioned before, the version is going to tell us what version we're using. The DOS, or I'm sorry, the DS, the differential serve or diff serve field, also known as like a type of service field, is 8 bits. That's usually used to set priority. This is typically used for telephones and things like that running on the network that need to have the lowest latency going across there. Then it goes ahead and specifies the total length there as well. Again, the maximum IP packet size is 65,535. You also have your identifications, your flags, your frame offsets, etc. You have your time to lives and your protocol, whatever you're using. So whether this is ICMP, the number 1, or TCP for 6 or UDP 17. In the header checksum, this is just going to be used to determine if there was any errors introduced during the transmission. Obviously, your source and destination IP addresses, and then you have some options and different padding that you can use to ensure that the field contains up to 32 bits. With an IPv6, you'll notice that there's only 8 fields as shown up here. Some of them are similar. So your version 1 is going to be the same. Your traffic class is going to be very similar to the DS bit on an IPv4. You have what's called a flow label. This is going to suggest that all packets have the same flow label, receive the same type of handling by routers. You have the payload length. Then you have your next header, which is going to be the equivalent to the protocol field in the IPv4. It'll carry the data payload type as well as the packet that it's carrying, enabling the network layer to choose the appropriate upper protocol. You'll have a hop limit. Typically, this is decremented by 1 every time that the router forwards a packet. When it reaches 0, the packet ends up being discarded. In an IPv6, this is a time exceeded message that'll end up getting sent back to the host, indicating the packet did not reach its destination. And as usual, you'll have your source and your destination addresses. All right, so different vulnerabilities that are susceptible for IP or internet protocol. You're going to have ICMP attacks. These are where we'll use ICMP echo messages or pings in order to discover subnets and hosts on a protected network and then generate a little DOS flood traffic, as well as being able to alter host routing tables. DOS attacks, these are typically where threat actors will use some sort of botnet or etc., especially with the DDoS attack that we have below that, in which they're trying to prevent legitimate users from accessing information or services. So on a dynamic or distributed one from down below, it's going to be a coordinated attack from multiple source machines, thus making it harder to shut down. On an address spoofing attack, this is where we're going to spoof the source IP address in an attempt to blind spoof or non-blind spoofing. Man-in-the-middle attack, this is where we're going to position ourselves between the source and the destination, transparently listening, capturing, or controlling the communication. They could be simply eavesdropping by inspecting packets, or we can alter those packets and then forward them on to their original destination. Session hijacking is going to be for gaining access to the physical network, and then we'll use a man-in-the-middle attack to hijack the session itself. So here's what an ICMP one will look like. It's developed to carry diagnostic messages in order to report error conditions when routes, hosts, and ports are unavailable. ICMP messages are typically generated by devices when there's a network error or outage occurs, but we also use this as the simple ping command. So this will generate an ICMP echo request packet. It can then be used to verify there's connectivity to the destination, provided there's not being blocked at some level on the destination itself. So on this side, threat actors can end up using ICMP for reconnaissance and scanning, which is what we would typically do if we wanted to find things on a network. But they usually go one step further and have the ability to use that for DOS attacks or DDoS attacks in order to create a flood and basically saturate the devices, causing them to have to respond and then get overloaded. So networks should have strict ICMP access control list filtering going on the network edge to avoid ICMP probing from the internet. In other words, we should not allow ICMP traffic from the internet side. The following is kind of a list of interest in there. ICMP echo request and echo reply. Those are typically used for host identification or verification, as well as the DOS attack itself. Unreachable is used in network reconnaissance, as well as scanning the network. We have mask reply. This is going to be used to map an internal IP address. The redirects are used to lure a target host into sending all traffic through a compromised device, thus creating a man-in-the-middle attack. And then ICMP router discovery is used to inject bogus route entries into the routing table of a target host. So for amplification and reflection attacks, these are going to be used as a technique for DOS style attacks. Their technique is called a Smurf attack, and it's basically used to overwhelm the target host. So amplification means that the threat actor is going to forward an ICMP echo request message to many of the hosts. Those messages are going to contain the source IP address, and then reflection, these hosts are then going to reply to the spoofed IP address of the victim who overwhelm it. So the idea is that, as you can see in the graphic, we're going to send a bunch of echo replies all the way down there, thus causing an issue for that system having to respond. It will end up causing resource exhaustion. Some newer forms of amplification and reflection attacks, such as DNS-based reflection and amplification, as well as network time protocol amplification attacks, are now being used. Again, it's a way to overwhelm the victim and exhaust all their resources, whether it's CPU, RAM, anything. Address spoofing attacks. These are going to be when we create packets with false source IP address information in an effort to either hide the identity of the sender or propose another legitimate user. Typically, these style of attacks are incorporated with another attack, like the Smurf attack we talked before. They can either be blind or non-blind. So non-blind is going to be when a threat actor can see the traffic that's being sent between the host and the target. That threat actor will use non-blinding spoofing in order to inspect the reply packet from the target victim and then determine the state of the firewall sequence, etc. It's also known as an authorized session or that type of hijack. A blind spoofing is where the threat actor cannot see the traffic that's being sent between the host and the target, and therefore it's typically done with DOS style of attacks. MAC address spoofing can be used when threat actors have access to the internal network. Particularly, they're just going to alter the MAC addresses and the switch tables in order to send traffic that would be destined for another party to themselves. Typically, when that switch will receive that frame, it'll examine that source address and then configure it onto the new one. Again, that's because this threat actor is saying they've changed their MAC address on this computer in order to match something that was already there. The switch will override its current CAM table, which is just a list of all the MAC addresses inside the switch itself. It'll then forward those frames to the destination target. Either an application or a service spoofing is another example. Threat actor can then connect to a rogue DHCP server to create a man-in-the-middle condition. So they'll come in here, they'll even pivot off your own internal resources, because then it looks like you're sending the traffic to an inside known source, which will probably help alleviate with ACLs within the firewall itself. All right, so for TCP and UDP vulnerabilities, within the TCP segment header, we have what is called the 6 control bits. Those are going to be right there in the center that you see, but you have the urge for an urgent pointer significant, ACK for an acknowledgement field, push, reset, syn, and fin. Because of these, TCP will give you reliable, right? So you've got your three-way handshake, et cetera, that's going to go on. What this is going to allow is you to incorporate acknowledgements to guarantee delivery, relying on upper protocols to detect and resolve any kind of errors. Typically, this type of reliability is going to be things that is used in HTTP or SSL, FTP, DNS zone transfers, et cetera. Those flow controls within TCP allow it to address a style of an issue. Particularly, rather than acknowledge one segment at a time, multiple segments can be used to acknowledge a single segment that goes inside there. And then as we talked about with the three-way handshake, TCP is stateful. Therefore, anything being transferred has to go through that. If it breaks the TCP connections, they renegotiate again and start over. So with that three-way handshake, this is typically what's getting attacked. So you initially send out your SYN packet. That SYN is received at the client. They send a SYN packet back as well as an ACK packet, which is going to say, I am looking for sync as well as acknowledging. And then the original host machine is going to send an established packet going back. So when we do TCP attacks and then specifically attacking those type of things, what we'll do is a TCP Syn Flood. And what this will do is just send multiple SYN requests to a web server. The web server sends SYN ACK replies and waits to complete the three-way handshake. However, a valid user, sends a SYN request and then the web server is unavailable. So we're overloading the resources of the web server as it's sitting there listening for all of the SYN packets that should be coming back to them in order to set up the three-way handshake. Because those packets will never arrive, it's going to sit there and have to time out. And if we're constantly flooding with new requests, then the server will be unable to respond to legitimate requests. Within a reset attack, this is going to be between two hosts. So what we'll do is we'll send a TCP Syn attack. We'll send a spoof packet containing a TCP reset on one or both ends. This is going to end up terminating the TCP session following a four-way exchange process that the client no longer has more data to send in the stream, sends a fin, ACK, and then does a fin and back ACK to the server itself. So what this is going to do is cause it to close the handshake and then have to reestablish that communication over and over and over by us sending reset packets going through there. So for session hijacking, this will be another TCP vulnerability. It's essentially when somebody takes over an already authenticated host as it communicates with the target. They must spoof the IP address of the host and then predict the next sequence number. So this is significantly harder to do, and then send an ACK in the next host. If successful, the threat actor could send but not receive data from the target device. And so it allows you to, if you look at your packets inside Wireshark, you always have your sequence number. You have to make sure you guess the correct number in order to pull off this type of attack. In the UDP segment, remember UDP is commonly used by DNS, DHCP, TFTP, NFS, SNMP because it is not a stateful packet. In other words, we don't have that three-way handshake. And therefore, UDP is technically or normally referred to as unreliable because it doesn't have any way of checking that the data was transferred overall. And so therefore the UDP structure is generally smaller than TCP. There's not as much overhead. And therefore there's certain protocols that want to make just simple request and reply transactions. UDP is the best choice. It has no level of encryption that can be added to it. I mean, you can add some, but it's not available by default. The lack of encryption means that anyone that can see that traffic, change it, and then send it to its own destination. So similar to a TCP flood, we have a UDP flood, and this is where we're going to try to consume all the resources on the network itself. Threat actor must use a tool like UDP Unicorn or the low orbit ion cannon. Those tools will send a flood of UDP packets, often spoofed by a host, to a server on a subnet. And that way the program will sweep through all the known ports, try and find all the closed ports. This will cause the server to reply with an ICMP port unreachable message. As there are many closed ports on most servers, this creates a lot of traffic on the segment, which ends up chewing up most of the bandwidth. And therefore, the result is very similar to that denial of service attack. All right, so to summarize this particular section, remember IP was designed as a layer 3 connectionless protocol. IPv4 has several fields. Some of those we're going to manipulate in order to pull off certain attacks. In the form of IP-related attacks, we have ICMP attacks, denial of service attacks, distributed denial of service attacks, address spoofing, man-in-the-middle, and session hijacking. We typically will use ICMP in order to carry this stuff out. It was originally designed and developed to carry out diagnostic messages and report error conditions. However, we can use different levels of that in order to overwhelm a target. A TCP segment and a UDP data frame information appear immediately after the IP header information. This would allow us in a TCP realm to perform port scans, Syn Flood attacks, reset attacks, and session hijacking. Remember, a UDP segment, also known as a datagram, is much smaller than a TCP, which therefore it's used by certain protocols to make simple request and reply transactions. And that covers this module.